Have you ever stopped to think about, well, thinking? I mean, you decide to reach for your coffee, and bam, your hand just does it. It all happens in a flash. It's this invisible spark of life that powers everything we do. So how does that spark actually travel from a thought in your head all the way to your fingertips? Well, today we're going to trace that journey.
So that's the big question, right? How does a single, simple idea, like I'm thirsty, become a physical action? It's an incredible journey, and it all plays out through this amazing symphony of electrical and chemical signals. So to get started, let's look at the highway this message travels on.
And that highway is the nervous system. You can think of it like a massive, super high-speed biological internet that connects everything. It's this huge network of cellular wires that are constantly zipping information to and from every single part of your body. And to really get how it all works, we've got to meet the messengers doing all the work.
Okay, first up, the anatomy of a neuron. Let's get to know the absolute star of the show, the nervous system's official messenger. This is the single specialized cell that's the fundamental building block for this entire communication network.
So this is it, the neuron. I know, it might look kind of complex, almost like a little tree with all its branches. But its job? It's surprisingly straightforward. This one cell is responsible for receiving, processing, and then sending all the messages that make you, well, you. It's the key to everything we're about to explore.
You know, when you really boil it down, a neuron's entire job comes down to just 3 basic steps. First, it's got to receive a message from its neighbor. Second, it has to maintain itself, just keep the lights on and stay healthy. And third, its whole purpose is to send that message on down the line. That's it. So let's see which parts of the neuron handle each of those jobs.
And if you look at it, you can see it's perfectly built for that 3-step job. Messages come in right here through these branch-like things called dendrites. Then the soma, that's the cell body, handles the maintenance and keeps the cell alive. From there, the message zips down this long tube, the axon, all the way to the end to the axon terminals. And that's where it'll pass the message on to the next cell.
Now check this out. A lot of axons have this secret weapon called myelin. So if the axon is an electrical wire, you can think of myelin as the rubber insulation wrapped around it. And this fatty coating, it doesn't just protect the axon, it makes the signal travel insanely fast. We're talking the difference between a nice walk and a bullet train. It's a huge upgrade.
All right, so that brings us to part 2, the electrical spark. We've met our messenger, the neuron. Now let's see how it actually fires. And when I say spark, I'm not being metaphorical. The signal traveling down that axon is a literal spark of electricity.
To get what's happening, you have to see the neuron when it's just waiting, at rest. When it's in this state, the inside of the cell is actually negatively charged, while the fluid on the outside is positively charged. So what you've got is basically a tiny biological battery, just sitting there, holding on to its potential, waiting for the signal to go.
And this is the moment it happens. It's called the action potential. As soon as a strong enough signal hits the neuron, these tiny gates on the axon just fly open. And look at this graph. All these positive ions rush into the cell, and the internal charge just skyrockets from negative to positive. That rapid reversal of charge is the electrical spark that shoots down the axon. It's incredible.
But here's a really critical rule for how this spark works. It's all or none. A neuron can't just fire a little bit. It either fires with everything it's got at full strength, or it doesn't fire at all. Think of it like a light switch. It's either on or it's off. There's no dimmer. And this ensures that every single message is sent with the same clear intensity. No ambiguity.
Okay, part 3, the chemical handshake. So our little electrical spark has raced all the way to the end of the line, to the axon terminal. But now it hits a roadblock. It can't just jump to the next neuron. So to bridge that gap, the message has to do something amazing. It changes from electrical to chemical.
And here's a close-up of that final hurdle. You can see the axon terminal of the neuron that's sending the message, and right across from it, the dendrite of the neuron that's receiving it. And that tiny, tiny little gap between them, that's called the synapse. And our message has got to find a way to get across.
So the synapse, it's just this incredibly small, fluid-filled space. Now, here's the problem. That electrical spark we've been following, it just can't jump across that liquid. So the neuron has to switch up its strategy. It's got to release these special chemical messengers that can physically float across the gap and carry the message.
And those chemical messengers, they're called neurotransmitters. So when our electrical spark finally hits the end of the axon terminal, it's like a trigger. It causes these little bubbles full of neurotransmitters to burst open, releasing them into the synapse to finally complete the last leg of the journey.
Okay, so how does the next neuron even know what the message is? Well, this part is brilliant. On its surface, it has these things called receptor sites, and they work exactly like locks. Each different neurotransmitter is like a uniquely shaped key, and it will only fit into a receptor lock that has the perfect matching shape. It's this beautiful, elegant system that makes sure the right message gets delivered to the right place, every single time.
And once that neurotransmitter key fits into the lock, it delivers one of two super simple messages: go or stop. An excitatory message is like a green light. It tells the next neuron to fire its own action potential and pass the message on. But an inhibitory message is a red light. It tells the cell to hold back and not fire. And it's this incredibly simple on-off balance that allows for all the amazing complexity of our thoughts and actions.
All right, let's zoom out for our last section, a symphony of signals. We've been following just a single spark on its tiny journey. But how in the world does this one microscopic event lead to something as rich and complex as a conscious thought?
Well, here's the thing that is just absolutely mind-blowing. This process we've been watching isn't happening just once. It is happening billions, no, trillions of times, every single second across this vast, interconnected network. Every single thought you have, every emotion you feel, every action you take, it's all the result of this massive, high-speed symphony of electrical sparks and chemical handshakes.
And so that leaves us with a pretty deep thought to end on. We've just seen that the most basic building blocks of our entire experience, everything from feeling the warmth of the sun on your skin to the complex emotion of love, it all boils down to this microscopic dance. So if every single signal is just a tiny electrical pulse, and every feeling is just a chemical handshake, what does that make you? That's something we're thinking about.